Good morning, viewers. Welcome back to my channel. At the end of this lesson, you shall be able to explain the following meaning of sound waves, the three categories of sound wave. Students shall be able to solve mathematical problems on sound wave. We shall also discuss about noise, and we would consider the acceptable range of noise and the possible ways to control noise. Let us move quickly down to the first question that we have here. What is sound wave? Sound wave is a longitudinal wave which propagates through a medium. Sound wave is a longitudinal wave which propagates through a medium. Hearing is a perception of sound, just as seeing is a perception of visible light. So hearing is a perception of sound. The human ear is sensitive to sound wave at the frequency range of 20 Hz to 20 kHz. So our ears can only detect sound at this range between 20 Hz to 20 kHz. The kilo here, don't be confused, is 1000. So the human ear detects sound at the range of 20 Hz to 20,000 Hz. So if we don't call it 20,000 Hz, then we call it kilo. Kilo there means 1000. Okay, so that is the audible range, 20 Hz to 20 kilohertz. That is the audible range. Below 20 Hz is the infrasonic range. The infrasonic range. So that one is below 20 Hz. That range is called the infrasonic range. And then above 20 kilohertz or above 20,000 Hz, we have the ultrasonic range. This is range, ultrasonic range. So this gives us the three categories of sound: the infrasonic range, the audible range, and the ultrasonic range. Okay, let's look at the next point. Sound waves are produced from vibrating objects. When objects vibrate, it produces sound wave. Even as I'm talking to you, my mouth is vibrating, and as such, sound is being produced. The example of infrasonic wave is the earthquake. The earthquake is an example of infrasonic range. So it's still a sound wave, but it propagates at a lower frequency than what we can detect. That is why sometimes something may be going on without the human ears being able to detect it. But some animals are always quick to detect it. That's why you see them begin to evacuate and leave that location where earthquake is about to happen. Example of ultrasonic wave are whistle. Some animals do whistle. Animals such as dogs can hear wave emitted at this frequency. So dogs can also hear wave at that frequency. However, other species of animals have different ranges of hearing. So animals do not hear the same way, even as humans don't hear like the animals. There are animals who hear differently depending on their perception. Bats, For example, emit clicks of ultrasound. You know bats. They emit clicks of ultrasound using frequencies which is above the 20,000 hertz, or which is above the 20 kilohertz. So they can detect nearby animals or insects by hearing the echo of this ultrasonic click. So when they give out this ultrasonic sound, it works under the principles of reflection. It gets to the object and reflects back to them, giving them the information about the object and the location. And that is how they hunt their prey. Let's move down to the next point here. Ultrasound is important in several applications. So sound wave that is greater than the frequency of 20 kilohertz is very important. It has applications. And this includes the probing of the interior surfaces of the human body. Could be the earth or the sun. So we have a picture here that is showing us something about probing of the human body. You now see the cord, the ultrasonic cord being connected to the human body here. Here you see the ultrasound probe placed on the patient's neck. This is the heart. This is the carotid artery. So you now see that this sensor is giving information about what is happening on this woman's body. So the ultrasound is of different applications, including the probing of the internal structure of the human body. So it gives information about the human body. You can as well give information about other objects like the earth and the sun as well. Ultrasound is useful in industries for non-destructive testing. When they say non-destructive, what does that mean? You don't destroy the object, but it gives information about the object. So this is being applied in industries. Ultrasound is used for non-destructive testing in engineering, in industries, such as testing the thickness of coating on metal. So you can get information from pipelines. You can get information from metals. Like these are engineers working on pipelines. Sometimes it may be that the pipeline has fault and all of that. So the ultrasound can as well help them to detect information about this pipeline without destroying it. That's what they mean by the non-destructive testing. Non-destructive testing. Let's check the next point here. In medicine, sound waves are far less destructive than X-rays. So sound waves are used in medicine because they are less destructive as X-rays and can be used to image the fetus in the mother's womb without danger of the fetus or on the mother. So you see this image here displaying the interior part of the mother's womb, and this is the picture. You see a baby in the mother's womb, and then the sensor is placed on the womb. And this works under the principles of reflection. So the reflected sound wave gives a report which is displayed on the screen, which will now tell the doctor about the position of the baby. Sometimes it could tell about the sex of the baby and all of that. Now, you cannot use X-ray in medicine in this case because X-ray it's a short wavelength and has the potential to damage cells in the life of the patient or in the body of the patient. So in medicine, sound waves are far less disruptive than X-ray and can be used to image the fetus. Okay, let us move down to the next point that we have here. Ultrasound is used to determine the velocity of blood in the arteries and to detect flaws. So it is used to determine the velocity of blood in the artery and to detect flaw. So you now see the signal on this meter here telling the doctor about the blood flow of the patient. Look at this. So this is the vein. This is the flow of the blood. And you now see that there are flaws, faults in this person's body. So you see it as a blue color. So the ultrasound has so many importance and uses and applications in medicine and in engineering. Okay, let's move down here. Production of sound wave. How is sound wave being produced? That is what we are going to discuss this moment. The sound of clarinet is produced by vibrating reed. Clarinet is an instrument, it's a wind instrument. The sound of a clarinet is produced by vibrating reed. The sound of a drum is produced by vibrations. The sound of piano is produced by vibrating strings. So those are sources of sound, things that can produce sound. But before I continue, I want us to know that those things that produces sound are the same sources of noise. The same sources of sound are the same sources of noise. When we get to noise, we will talk about that. A speaker produces sound wave by oscillating a cone, causing vibrations of air molecules. So whenever you see the loudspeaker produces sound wave by vibrating the cone, and the cone now mounts pressure on the air particles as well. Okay, let's read what we have here. A speaker vibrates at a constant frequency and amplitude, producing vibrations in the surrounding air molecules. As a speaker oscillates back and forth, it transfers energy to the air, mostly thermal energy. But a small part of the speaker's energy goes into compressing and expanding the surrounding air, creating slightly higher and lower local pressures. Okay, so let's look at the figure below so that we understand what we're trying to say. This is a speaker. The same speaker is here. So you now see that the pressure from vibrations of the cone of this speaker affects the air, causing compression and rarefaction. So this compression is where you have the HP, and the rarefaction is where you have the LP. So the HP here is a point where you have high pressure is compared to the crest of the transverse wave. And the LP here is where you have low pressure and could be compared to the trough of a transverse wave, or should I call it a sine wave. So you now see that the compression here is higher, while here we have extension, or we call it the rarefaction. Let us go back to what we were reading. These compressions, high pressure region, and rarefaction, low pressure region. I've talked about that. So when you have the compression, is where you have the high pressure region, and then the rarefaction is where you have the low pressure region. Okay. We don't have study questions yet, so let me remove this. There are three categories of sound waves: the infrasonic waves, the audible waves, and the ultrasonic waves. We have already talked about that. So we move to the next thing: speed of sound in various media. So the way sound propagates in different media is not the same. In gases, sound has different speed depending on the temperature. Like here, if it's propagating through the air at 0 degrees Celsius, then the speed of sound would be 331 meters per second. So that would be the speed, or you call it the velocity of sound. So the air in air of temperature of about 100 degrees Celsius, sound propagates at the velocity of 386 meters per second. So it is faster in high temperature than in lower temperature. Sound in hydrogen, 1290, oxygen, helium, in liquid, and in solids. Okay, let's go down. Energy and intensity of sound. So we're going to talk about energy and intensity of sound. The average intensity of a wave or sound wave, the average intensity of a sound wave on a given surface is defined as the rate at which energy flows through the surface. The rate at which energy flows through the surface per unit area. The rate at which energy flows through the surface divided by the surface area. The rate at which energy flows through the surface per unit area. If we look at delta E slash delta T, you now see that this represents power. That represents power. Okay. So, rate of energy flow all over T, all over the A. Mathematically, we can write it as, let's go to the board so that we really understand what I'm trying to say. Stay on the line. I'm still with you. I'm still with you. Okay. So we have delta E all over T, rate of energy flow per unit area. So this is all over A. Now, mathematically, it's not proper for us to leave this way. So we put over 1 here. Now, this can as well be written as change in E all over T. Now, here we have A over 1. It's not proper keeping it this way mathematically. So the next thing we are going to do is to rotate the denominator. When we rotate the denominator, this division line here will change to multiplication. So another way of writing this expression is times. When you rotate this division line changes to multiplication. So this will now be times 1 all over A. So this is the expression we had. Let us go back to what we were doing. Okay, welcome back. So the average intensity of a sound wave on a given surface is defined as the rate at which energy flows through a surface per unit area. The rate at which energy flows through a surface per unit area. We take this as equation 1. Energy flow all over T represents power. So in place of E over T all over A, we just replace P. Let's go to the board so I show you what I'm trying to say. So this is the rate of energy flow per unit area all over A. So we have here rate of energy flow per unit area. This expression represents power. So we can write this expression as I equals to P all over A. That's another way of representing this expression. So we call this equation 2. What's the SI unit of power? Watt. What is the SI unit of area? Meter square. So that gives us the SI unit of intensity, which is watt per meter square. Let us go back. So that is how we got the SI unit here, watt per meter square. All right, let's go down. where P is the sound power passing through the surface. So P is the sound power passing through the surface. The faintest sound, the lowest sound, the faintest sound the human ear can detect at a frequency of 1000 Hertz have an intensity of about 1 times 10 to power should be minus 12. Should be minus 12. Okay. So I'm coming. Okay, I think I have corrected it. So the faintest sound that the human ear can detect at a frequency of 100 Hertz have the intensity 1 times 10 to the power minus 12 watt per meter square. That is the least amount of intensity the human ear can detect. This intensity is called the threshold of hearing. So it is a constant. The constant, the faintest sound the human ear can detect at this frequency is 1 times 10 to the power minus 12 watt per meter square. Please memorize that expression. Don't forget, because we are going to use it in the calculation. The loudest sound the ear can tolerate have intensity of about 1 watt per meter. So the loudest sound per meter square, sorry. So the loudest sound the ear can tolerate have an intensity of about 1 watt per meter square. So we call this loudest sound the threshold of pain. The threshold of pain.